Good evening.
Yes, good evening, Marcel. So this is now a video for the third assignment.
So this is an assignment where we wanted to make use of a queue for solving some problem.
That's right.
Turns out that it's a great assignment to talk about various ideas related to programming, to computing.
Yes, that's right. I mean, this assignment was really meant initially just to use a queue, and then as we went through it, we realized that we could introduce several concepts that are going to be quite useful. Some of them we are going to see, we're going to cover in much more details in the coming weeks. But those concepts are very important for you as programmers anyways.
So let's look at the PDF. So it's always important to remember what the learning objectives are that allows you to focus your attention on the important things, the things where you're going to get marks, the elements as well that you may find in a final exam, for instance. Okay, so we've seen something in the midterm that came from an assignment.
That's right. Okay,
so we're going to implement some algorithm and it's going to be using a queue. In doing our work, there will be this concept called deep copy that's fairly important for programming. You can't go very far in programming unless you clearly understand this concept of deep copy. In Java, it has severe implications where you can make big mistakes. Maybe some of you will be experimenting the kind of errors that are generated if the deep copy is not properly implemented.
That's right. Actually, we hope that you will. So you will learn from it here.
Yeah, it's always better to learn about these things in the concept, in the context of your classes rather than on the workplace.
That's right.
We've learned about exceptions, so let's throw exceptions when it's appropriate. So it would be a good idea to, every time you're starting coding some method, to think that there are these preconditions. So you have to make sure that the values for the parameters are valid and that the state of the object is proper so that it makes sense to start executing the statements.
That's
of this
right.
method.
So each method has some assumptions regarding when it can be executed and under which circumstances, and if those are not met, then there is no point in proceeding, and instead you should simply throw an exception to stop the process right there.
And with the midterm, we've seen that it's not always obvious to think about all the possible preconditions. Okay.
All right.
So this is about a game, a puzzle called Instant Insanity. So I have my cube made out of paper.
I have my cubes, which are the real ones.
These ones are almost free. Easy to find.
But I did find those ones.
Where did you buy it?
Well, just downtown, actually. Yeah. Just downtown.
Okay. So the game is relatively easy to explain. So the puzzle is
right.
So it's made of 4 cubes.
So you have 4 cubes, and each cube has a combination of 4 colors on the 6 faces of the cube. And so if you stack them up like that, so you have a stack of 4 cubes. Well, they are the colors. So in these two sides here, they have 4 different colors. But if you look at this side here, the colors are repeated.
Yeah, blue and white are repeated,
and it's the same thing here. So here the goal is, can you stack up those 4 cubes so that the colors are not repeating? another way to put it is, you know, do you see all four colors on each of the four sides? So the only thing that matters here is the side of the stack of the solution. So four sides, four colors per side, or no repeating colors. We'll see that it's going to be easier to think this way. No repeating colors on either of the sides. So that's the goal.
Yeah. So if we look at the PDF again, although we're not providing any classes this time, any implementation for you to start with, we're still providing you a framework. Yes. We're suggesting that, well,
we're not suggesting you, we are asking you.
We're asking you to have a class cube, a class solution, and a class solve, as well as the enum type color.
Right.
There will also be a queue implementation in there. So it's important to think globally about these three classes. So the class cube will be modeling each one of those cubes. They're unique cubes. The class solution will be a container to store cubes, and the class solve will actually use one of two different algorithms for solving the problem. So this assignment has a lot of bells and whistles, opportunities to introduce new concepts. One of them is an enum type. We didn't talk about enum types so far, but it's a great mechanism or great syntax of Java to create constants that are typed. And as always, when we have the idea of having strongly typed constructions in our program is to detect errors early on at compile
time. Yes. So here we can use an enum like that to define what our colors are in this case, and we'll be able to check that. So as we have never seen an enum before, there is here in Annex B an explanation about what those enums are.
So the example shows that often programmers are using constants of type int to represent symbolic information like Monday, Tuesday, the days of the week or the month. But in doing so, we're giving very little information for the compiler to detect some kind of errors.
Like because those are int.
Because those are int. So here I made an error. I've assigned January to the variable day, and because January is of type int, the compiler has no clue, says it works. We're providing here a Java solution, so we're declaring two enum types, day and month. And what we see here is if we try to modify this particular line here of the program and we replace it with this, where we're trying to assign the constant January to day, the compiler now will be able to detect this error because days and month are two distinct concepts.
Right.
Maybe the one thing I wanted to mention with this example was that here enum, the two enums are declared as in a nested fashion. They're declared inside the class E2. I could have declared day and month outside in their own file. So there could be a file day.java that would have this particular syntax here.
Yes, and so if you put it outside like that, it makes it available for every other class directly that are in the same package. So in this case, that's what we ask you to do. So color is in its own file.
Yeah. So here, the next concept is the cube. So we have a class cube to represent the cubes in this puzzle. Each cube has 6 faces. There's a constructor that is used to initialize a specific cube. So it receives the reference of an array of colors, and the information is provided in a specific order. So the first entry of the array is the color for up, then the color for front, right, back, left, and down.
Yes.
Accordingly, there are getters, so you can return the color for up, down, front, right, left, so on and so forth. And there is a toString method that will generate a string representation of the current orientation of the cube.
So that's well, actually this is coming. The idea of the current orientation is going to be very important here. So a cube has not only colors on the faces the way it has been specified by the constructor, but it also has an orientation in space. So at a given time, the cube that has this cube here with this color could be like that, could be like that, could be any possible position, and we need to track that.
And it's not that it's extremely complicated to think about all these 24 orientations, but at the same time, it's not trivial either.
Yes,
So
if I ask Marcel to enumerate the position like that, well, especially here with the color that are repeating is going to be pretty tough, but even with his magic cube here, it will be pretty difficult, you know, once you're at position 14, to try to give me another position and be sure that you are not repeating position that you have already seen.
So when implementing the generate and test and the breadth first search, it would be pretty challenging. It would be awkward to have to think about, to memorize in which orientation the cube was and to try to generate the next possible orientation for the cube. So instead, what we're suggesting here, and again, we're asking you really, what we're asking you to do is to implement a set of methods that will handle the flipping and the rotation of the cube.
So something that we can use to ask the cube to go through all the possible 24 positions from outside without having to worry about how it's done.
So we will first explain how this works from an outside perspective. So when you're outside of the class cube, you can ask this cube, if I were to move you, to flip you, to rotate you, can I do so without revisiting one of the orientations that I've already seen
From you, yes.
in the little while? In the little while is since the last reset of the cube. So the mechanism that we're talking about will make it very easy from outside to visit all 24 orientations.
Right. So we have already mentioned the method reset. So you start from a cube that you have reset. And then you have the method next. And next will basically, every time you ask a cube to give you its next orientation, it's going to provide you something you have not seen before. So you should be able to ask a cube for its next orientation exactly 24 times, because there are only 24 orientations. So you don't have to, you could keep track of how many times you have asked the cube, but in fact the cube can tell you that by asking the asNext, by calling the asNext method, which will return true if you have not seen all 24 orientation since the last reset.
Correct. So there's a little piece of code here that shows how it works. So we're creating a cube. We're making sure that the cube is in the original orientation, the one that it was when it was created. And then we're asking this cube, if I were to call next, would it work? Would you be able to move without going back to an orientation that I've already seen? So that's the whole idea.
Mm.
So while C dot has next is true, go inside the while, flip. So
C dot next.
the call to next will somehow flip the cube in a way that every call to next generates a new orientation, an orientation that has not been seen before, and we can do this only 24 times.
Right.
Why 24? Because if you think about this, a cube has 6 faces. If we're using my paper cube, where I have numbers on the faces, there's one that it's called top. There's one that's called front, so on and so forth. So there are 6 faces. So there's 6 ways to select the top. Once we have a top selected, we can do 4 rotations, well, 3, and the 4th one will bring us back to where we were. And then we can select a new top. There's 3 different rotate. The 4th one brings us back. So that's for the 24 orientations.
Right, so 4 positions for each face on the top.
So this code goes through all these 24 orientations, and to really exemplify how it's meant to be used, we're doing this twice. So we're calling reset, and then you see that we can go through the 24 orientations again. So that's from outside. From outside, hopefully you appreciate how easy it is to go through the 24 transformation. You just ask this cube, please go back to your initial state. As long as next is true, call next, it's going to do some magic and flip.
Right. So now we need to implement that inside the cube.
Yeah, so now we transport ourselves inside the class cube. So we tried to imagine a way to describe how we can transform this cube. And we came up with rotate, right roll, left roll, and the identity. So these are not necessarily methods that you have to implement.
No.
It's a language to describe how we can transform the orientation of a cube. So there's a rotate.
So rotate, if I am a cube like that, so I have this on the top. If I want to rotate, I would just flip it along this axis, top bottom, by a quarter of a turn. Rotate, rotate, rotate. So if I call rotate 4 times, I am back to the position I was in.
There's right roll.
So we're just going to flip along the axis front back, one side, so to the right. Left roll.
Left roll is brother of right roll. And identity is an operation that brings the cube back to its original state, or where the faces have all the original colors on them.
Right, so when you created the cube, it already had a position, and whichever that position was, every time you ask it to go back to the identity, it will go back to that position. Mm. So this orientation here, these operations, the first 3 are defined with respect to the current orientation. Mm. So it changes from where you are to something else, while the identity is independent from your current position. It just goes back to the original position regardless.
And here we're proposing a list of operations. If you do these operations in that order, you will visit all 24 possible orientations, and only at the end will you go back to the original state.
Actually, you would not. If you were to continue if you were to do anything after that, you will necessarily go back to the position you have seen before.
So it starts by placing the cube in its original state. Then it's doing rotate, rotate, rotate 3 times, followed by roll, followed by rotate, 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 roll, etc. And with this sequence, if you think about it for a little while, you'll see that you go through very systematically all 24 orientations of the cube.
Right. And obviously there are many other possible operations. We try to stick to those 3 plus identity because they are very simple. But you can imagine many different transformations, a twist, any kind of flip that you want, and that would have worked as well. But these ones are just simple.
Yeah, and to a certain degree, it's not important from outside. As long as you're
outside, you don't care.
As long as next, the repeated calls to next are allowing us to go through all of the 24 different orientation, we're good.
That's right.
But here's a recipe that does it.
So this perhaps is an opportunity to mention something here. So every time we have these videos, we are insisting that you should compile. But really compiling is just the first step. It's sort of the minimum requirement. If it doesn't compile, well. But if it does compile, it doesn't mean that it's working. And when you are going to do this assignment, so you are going to work on your cube, and yes, you are going to compile it. You are sure that this file compiles. And then if you move on to the solution, make sure that that compiles, and then to the solve and make sure that that compiles, and then only try to get all that together and see if this is going to work. Then you are going to have the bugs from cubes and the bugs from solutions and the bugs from solve that are all going to come together, and it is going to be fairly difficult for you to understand where the problem is coming from, because some of these bugs here are going to be a bit nasty, really. And so we want to stress the fact that it is going to be important from now on for you, whenever you create such a class here, to try to test, to debug, to test the class, your implementation, as much as possible before you try to use it in the context of another class. So you're going to do what we sometimes call unit testing, where you want to try all these methods, and you want to take these objects cube here and really shake them every which way you can think of, to make sure that this is working before you try to get that cube into a solution, into your class solution, and see if that class solution works. So it's just a little trick here that I will strongly advise you to follow. Spend some time testing this class independently from everything else.
And that's what we did for our own implementation. We wrote a class test cube that would really test all of those methods. You make sure to keep that around so that if you make a change to your class cube, you run the test again to make sure that it still passes all the tests.
That's right.
That's what we do in software development. We keep these tests around, and whenever we're making changes, we rerun the test to make sure that everything works. And many of the issues that you will be facing will actually come from this concept that we will introduce in the coming minutes called deep copy. So we're having a method copy here that has to return a deep copy of the cube. So guy-vincent, what's a deep copy?
So this is a new concept, really. We have been talking about copying references, copying variables, but here you want to copy objects. And when you copy objects, if you think about it, you are going to have to worry about what is happening to the reference that are the instance variable of that object. So here we have an example, and so we're going to go from what we call a shallow copy to what we call a deep copy. So here you have an object which is referenced by A here, and it has a title, a time, a remainder. The remainder is a primitive variable, but title and time are two references. So title is a reference to a string, time is a reference to some other object that has itself two reference variables, start and end, and they are both time object of some sort.
So now if we were to create a copy of the object designated by A, we would obtain the object below.
That's right. So here we have already. So there is the copy of the reference B equals A. You would not obtain that if you were to write simply B equals A. You would have B referencing the same object that A is referencing. So here you have put some work into copying the object itself instead of the reference of that object. But what you have done is gone to that object and duplicated all of its instance variable. And so that's what you have.
So when the instance variables are of a primitive type, the copy actually copies the value itself. So here, reminder has value 15, and the instance variable reminder of the object designated by B has its own copy of reminder.
That's right. So if you change the remainder of A, it's not going to change the remainder of B after the copy.
However, if we do a shallow copy for reference variables, so here if I copy the title of the object designated by A into B.title, if I literally say something like B.title equals to A.title, what I get is that A.title and B.title are both pointing at the same object.
Right, so you have two references, but they have both the same value. They are both referencing the same object.
Same thing if I do B.time equals A.time, what I get is that these two reference variables are pointing at the same object.
That's right. So here what you have done is a shallow copy of this object. In many cases, that's not really what you want. I mean, it might be what you want, but you have to understand that there are a lot of consequences from that copy here. As long as you are just looking at the object pointed at by A and the one pointed by B, well, those are two separate things. But if you start following any of these references that they both have, then you are sharing the object.
So in particular, here if I change A.time.start.hours, well, turns out that I've also changed B.time.start.hours.
Right.
And that's a problem.
If that's not what you wanted, then that's a problem. And that is because you did a shallow copy. So if you do want really these things to be deeply different, then you want to do a deep copy.
So what deep copy is about is not only we duplicate the object designated by the initial reference variable, like was done here, but in Cascade we continue the work. So if title is a reference variable, then we need to duplicate this thing, which is what we're getting to the right here. So we duplicated title so that B.title points at an object that's not the same as A.title.
That is a copy of the object A.title that is pointed by A.title.
Likewise, time is a reference variable, so the object designated by time was copied, and because a time object here, or the object that's here has a start variable that's also a reference variable, then the object designated was also copied. And now we reach a point where all these variables are of a primitive type, so this is where the cascade of event stops.
That's right. And so now with this deep copy, you really have two completely different series of objects pointed by A or by B, and they live independently from one another. If you change A, that has no impact on B.
Yeah, so A.time.start.hours is independent of B.time.starts.hours.
Right. So that's a fairly generic concept in programming in general, and this idea of deep copying objects is important in any object-oriented programming language. Some of these languages do come with direct method to do that, direct solution for that. But here what we want to do is, well, we like to do it manually, really. We want to feel things. And so we are going to do our copy ourselves, our deep copy ourselves.
And that's going to be very important for this assignment, because whenever we will be creating independent solutions, we really need to have each solution to have its own cube. We don't want to have that we're calling next on a cube from one solution, and whoop, the other solution changes at the same time.
Right. That would be a very common bug to have. It would be pretty annoying.
So here the method copy will clone the object to return a deep copy of it, and the constructor will initialize the newly created cube to be an independent copy of other.
Right. And so we ask you to do that yourself.
Okay, so solution should be straightforward. A solution is a container for cubes. So in a solution there can be 1 cube, 2 cubes, 3 cubes, or 4 cubes.
Right. So you build your solution, and so when you create a solution, you have two ways of creating a solution. You can create a solution passing cubes. So that's the first constructor, and yes. So if you pass this cube, this array of cubes to a solution, that's where this idea of making sure that the cubes that the solution is having should not be the same as the cubes that another solution is playing with, because those solutions, they are going to try to find something, and you don't want the work done on that solution to impact negatively the work done on that other solution.
There's a second constructor, and for now it may look a little bit bizarre, but it should prove to be very useful when you will be implementing your breadth first search. So we can initialize a solution by receiving the reference of an existing partial solution, and we're adding to that solution a cube.
Right. So I have a stack. This is my A solution. I can ask, can you create a new solution using that as the base? And here's the cube. And remember, a cube is always in a particular position. So using that cube in its current position on top, extend the solution. And that is going to be a new solution. Hint, a new solution. These cubes of the first solution and the cubes that are in the new solution should not be the same.
Yeah, so they will have the same elements in the same order, but they will be independent.
Right.
Okay. So a solution is a container for cubes, so we have methods to know how many cubes there are. For debugging, it might be useful to obtain the reference of each one of the cubes that are in a solution. And then the methods that will be important for your algorithms for solving the instant insanity problem are isValid and isValid that receives the reference of a cube. So remember that isValid is a instance method of a solution. So given a solution, you can ask, are you valid?
Right. So this is a solution, and it is not valid because the green is repeated twice on that face. And anyway, that's enough for it to not be valid.
Then there's a method isValid. Again, it's the method isValid of a solution, but it receives the reference of another cube. So here, guy-vincent has 2 cubes.
And so I have a solution, and that solution is valid right now, because if you look at all possible faces, you have no repeats on the face. So each face has no repeat of colors. So the question is, if you are going to add the cube next on top of that solution, is it going to remain valid?
Yeah. And here on my side, there was green and green.
Right.
So not valid. Okay, so then in the class solve, we're going to be comparing 2 different algorithms, and we would like to compare them according to some kind of measure of how efficient or rapid this method is. And to do this, we're going to count how many times the method isValid was called.
Right.
And we're going to do the method here, the count that is returned is the total number of calls for any solution that was created during the execution of the program.
Yes.
Since the last call to the method reset number of calls.
Right. So that's not the number of calls to isValid to a particular solution. It's across all solutions.
So there might be something in Java that you can find useful for that.
Maybe.
So finally, the class solve is where we're hosting the methods for solving the problem. There are 2 methods for solving the problem. One is generate and test, which is a method that should be easy to convince yourself that it will find all the solutions, because it's enumerating all possible solutions. So it really is
also positions in the solution object. So you will get 1, 2, 3, and 4. Okay, 1, 2, 3, and 4 cubes, and then you will ask, is this a valid solution? No? Okay, let me generate another one. What about this one?
So you will very systematically
It may take a while.
go through all 24 orientation for the first cube, all 24 orientation of the second one, third one, fourth one.
And each time, is this valid?
And you're asking the question, is it valid? Only when you created a complete solution. So yes, it's very systematic. Yes, it should find, if well implemented, all the possible solutions. However, it's very easy to see that it's not a very efficient way of solving the problem, because if I start with a solution that is already not valid,
and I continue that solution, and I say, okay, this is not valid, what about this one? Oh, and what about this one? And what about this one? So I have 24 ways of making that already invalid solution still invalid. And then I have 24 ways of moving this guy and asking again 24 times, is this valid? And all of that is a complete waste of time.
Yes, so if the starting solution is not valid, there's no way that I'm going to add cubes to the tower and suddenly I'm going to get a valid solution. So really what I should do is start with all 24 possible orientation for the first cube, and these ones are for sure valid because there's only one cube. Then I'm adding to each one of those 24 orientations a cube. and I'm adding the cube in all 24 possible orientation. As soon as I find a combination like this that's not valid, well, I should show one that's actually not valid, then I should throw it away, because there's no way that I'm going to end up with something useful out of that.
By throwing it away, we mean here that there's no point in adding a third cube on top of it.
So that's what the breadth first search is doing. It starts with an empty cube. We're now adding all the possible orientations for the first cube. We're grabbing an element out of this cube. We're looking at all the possible extensions, so meaning all the ways there are to add the second cubes, and there are 24 ways to do that. Every time I realize that this partial solution is not valid, discard, in the sense of do not add the solution to the rear of the cube. Do this very systematically. Take something up from the front of the cube, look at all possible extensions. Those that are valid go to the rear. Do this work systematically. Will allow us to enumerate all possible solutions. A solution that solves the problem is a solution that contains 4 cubes, and all the faces of this tower contain all 4 colors, or another way to say the same thing is that there are no duplicated colors on the 4 external faces of the tower.
That's right. And so this idea of using the cube to try to build a solution should remind you of what we have been discussing in class regarding the labyrinth, where we were trying to find a path in the maze, and we were doing that, and we were using the cube for that, and it was very similar to that. In fact, it's really almost the same thing at that point. There is one difference though, which is, and we could have done that with the maze as well. In the maze case, we were interested in finding the first solution. In fact, the first solution was had some properties that was interesting. But anyways, we just wanted one solution. And in this case, although we could be asking you for the first solution you're going to find, what we want really you to produce are all the solutions. So you are not going to stop after finding the first solution. You are going to keep going until you run out of options.
And here, as Guy-Vincent was saying, the solution that you're going to get, the implementation that you will be producing, will be very similar to what we've done in class, and that's thanks to the fact that we created these operation next and has next. We really pushed the knowledge about how to do these transformation, these extension was pushed inside the class cube, so it's making the generate and test and breadth first search very simple.
That's right.
So
you should be able to run these things and get here. So here we have 2 things. We have so generate and test is going to display the number of time that the isValid method is going to be called during the resolution, and it's also here the code that we show here is going to provide the time. So it will tell you how long it took for the first method and for the second method to find all the solutions. Okay, so it used to be, when some of us had long hair and everything, it used to be the case that this would take a while. On my computer, actually I didn't even have a computer, on the computer that I could use during my studies, if I were to do that, it would take reasonably long to generate all the solutions. Nowadays, not so much. You could probably do that on your phone in a fraction of a second. And so that's why we are not really relying on time here, but really on the number of calls to this method isValid, to show that there is a net gain in going from the exhaustive search to the improved search with the breadth-first search. Now this is fast because this is in fact a fairly simple game in terms of computer science here. It's just 4 cubes. If you add 20 or 100 cubes, then it would take forever, even on your very fast machines of today.
So there's also a bonus question for this assignment.
That's right. So here, the first two things, the first two methods that we are talking about, one is more efficient than the other, but they are going to produce the same thing.
Yeah.
They should.
So whatever is the number of solutions that you're producing with the generate and test, you should find the very same number of solutions using the breadth-first search. However, turns out that we were not so clever in the way we've solved the problem.
That's right.
There's some redundancy here. That's what we're saying. There might be some symmetry in the solution. So we're asking for your help to actually reduce the number of solutions that are produced.
Right. Some of these solutions are not adding anything. So, but we don't know which ones.
So if you go on the internet, you will find recipes.
On the internet?
Yeah. On this big network. So I'm sure everybody's familiar with the Rubik cube, and if you go on the internet, at least that's how I was solving the cube. I was using these recipes where I would know how to move one cube to the front or to a face or something like that. So if you go on the internet, you will find recipes that will tell you precisely how to...
This guy this way, this other guy this way, so on and so forth. Well, that doesn't work, but you know, never believe what you see on the internet. But anyways, it's going to give you a solution.
And if you implement just that, well, we don't care. It's not, it's not worth any number of points.
Not even the bonus ones.
We can go on the internet ourselves and find this.
Yeah, I can ask my son.
So what we're asking here is actually how can you transform these algorithms so that they don't produce these solutions that don't bring anything new to the problem, to the game.
That's right. Yeah. So that's a bonus question. So only if you have time.
Yeah. So as always, please submit a zip file.
Right. We have got several RAR files, 7S something files.
Yeah.
GZ.
And it's really not because we're that picky. It's because because in real life, programs have to have a certain structure. If you do some web development, you're going to be required to create some archive that will have a very specific name, specific structure. Otherwise, the application will not deploy on the server. So those are very important. Just like you have to have all the semicolons, you have to have all those parentheses and things like that. You have to have the files in the right place in a zip file. So you will be submitting your color.java, the cube.java, solution.java, solve. You have to also have some implementation of a queue so that we can run actually the program straight out of unzipping your submission. We'd like to have a Java doc directory, and we'd like to have your student info file with all the information filled in there.
Yes, don't forget that. I've seen again several students who have submitted, working 2 students submit, and one of them is submitting, and they forgot the student info, they didn't include a README, and they did not follow the convention for the name of the file, and so we have no way of knowing who is the other student working there. It's not a good idea.
Okay, so I think we've said it all.
I think we are ready to go here, and we are also open for business on Piazza. If you have any questions,
Yes.
You just go there, and we'll try to give you an answer quickly.
All right.
Thank you.
Bye now.